Hello and thank you for watching my video. In today's exercise I'll be going over OSPF. I will review the different OSPF router types. We will look at the OSPF link state advertisements. I will review OSPF areas, and we will configure a single OSPF area. After we make router configurations I will touch on DR and BDR elections. And we will run debug on OSPF packets. For ease of demonstration, I will be using Cisco's Modeling Labs. You can purchase at cisco.com or sign up for some free lab time at developer.cisco.com. Under DevNet Resources, Sandbox, Networking, I highly recommend giving it a try. OSPF stands for Open Shortest Path First, and it's a link state routing protocol that's used to help routers talk to each other and figure out the best way to send data from one place to another. OSPF sends information about its directly connected links to all of the routers in the autonomous system. Think of it like a road map. When you're trying to get from one place to another, you want to find the shortest and most efficient route. In the same way, routers need to find the shortest and most efficient path for data to travel between networks. OSPF helps routers do this by creating a database of all the routes that are available, and then using Dijkstra's algorithm to figure out which path is the best. It takes into account things like the speed of the connection, the number of hops between networks, and the amount of traffic on each route. When a router joins an OSPF network, it sends out a message called an LSA to all the other routers, letting them know that it's there. The other routers respond with their own messages, and together they build a complete map of the network. OSPF has 4 router types. The backbone router. It has at least one interface in the area 0 or backbone area. The internal router. It has all of its interfaces in a single area. The ABR or area border router. It has at least one interface in the backbone area and at least one interface in a non-backbone area. And the ASBR or autonomous system border router. It connects to an area as well as an external autonomous system. As mentioned previously, OSPF uses LSA or link state advertisement packets. This is how it builds the topology of the network. These are the 5 types of LSAs that we are concerned with. OSPF uses areas to simplify administration and optimize traffic and router resource utilization. There are 5 OSPF area types. 1. The backbone area. This is the core of a OSPF network, and we use area 0 to designate it. All other areas must connect to this area. All 5 OSPF packet types or LSAs are passed in this area. 2. The standard area. All 5 LSAs are passed in this area. 3. Stub area. This area does not accept external routes and uses the default route to reach an external network. It passes LSA types 1, 2 and 3. 4. Totally stubby area. The area does not accept external routes and does not accept the link information of other areas outside of its area. If it wants to reach a network outside the area, it will send out the message through the default route just like the stub area. But since the default route is sent using Type 3 LSAs, the completely stub area does not allow ordinary Type 3 LSA packets. It supports this type of LSA with default routes. This area supports Type 1, Type 2 and Type 3 LSAs with default routes. 5. Not so stubby area, sometimes called NSSA, is actually derived from the stub area. It means that in the case of a stub area, it also has to send external routes to other areas' ability. This area supports the 1, 2, 3, and 7 type LSAs. In this exercise, I'm using a very basic OSPF topology. We're only using area 0, so all 4 routers will be in the backbone area. Let's start with router 1. I've only set up the links. We will need to change the host name. I will also turn off IP domain lookup. Now I will configure the interfaces and use the IP addresses in the spreadsheet I made earlier. You can see each router has a LAN and a WAN interface. I'll add the link description. And let's configure the WAN interface. 10.10.0.1 with a 24-bit subnet mask. Add the link description here and we can repeat the interface configurations on the other 3 routers. 10.2.0.1, 255.255.255.0. Ten dot 10.0.2, 255.255.255.0. Let's run a quick ping test across the WAN link. It's good. On to router 3. IP 10.1.0.2 with a 24-bit mask. IP 10.20.0.1 also with a 24-bit mask. And finally router 4. The LAN interface. Let's do a few ping tests. A quick check of the IP addresses with the show IP interface brief command. Now I'll go back to router 1 and start the OSPF configuration. The command is router, OSPF and process. For this example I'll use 100 for the process. Now we add the networks. The command is network, IP address 10.10.0.0, then the wildcard mask of 0.0.0.255 since we are using a class C address. Then its area and the area number, we are using area 0 for all networks in this exercise. And now the LAN network. Area 0 for both interfaces. So if this router has only 2 networks and both network interfaces are in area 0, we need to repeat the OSPF configuration for each of the routers. And the last one. Router 4. Let's run a ping from desktop to verify a layer 3 path. Looks good. Let's check the route table on the routers. Here we can see the 2 OSPF learned routes, designated as such with the O next to them on the left. I'll check the other routers to make sure they have OSPF routes in each of their routing tables. You can also tell this is an OSPF route by its administrative distance of 110. And finally router 4. All of the route tables are updated correctly with the OSPF routes. Let's run the show IP OSPF database command. Each router should show 4 router or type 1 LSAs and 4 network type 2 LSAs. Before we go any further, we need to discuss what the OSPF DR and BDR are, and what they do, and how they become a DR or BDR. DR stand for designated router and BDR stands for designated backup router. There is one of each for each broadcast network type like a LAN. The DR and BDR serve as the prime point for exchanging OSPF routing information. Each non-DR or non-BDR router will exchange routing information only with the DR and BDR, instead of exchanging updates with every router on the network segment. The DR will distribute the topology information to every other router inside the same area, which greatly reduces OSPF traffic and increase resource efficiency. Based on the network type, OSPF performs an election to make one router to be the DR and one router to be the BDR. On multi-access broadcast networks, such as LANs, routers default to elect a DR and BDR. By default, routers running OSPF are elected DR and BDR based on two rules. Rule 1, the router with the highest OSPF priority will become the DR, but by default all routers have a priority of 1. Rule 2, if there is a tie, the router with the highest router ID becomes the DR. And the router with second highest router ID will become the BDR. The router ID can be configured, or by default it is the highest IP on the router. Going back to our network. Because the topology has two broadcast networks, the LANs the desktops are connected to, means we should have two sets of DR and BDRs. Let's take a look. For LAN 1, I'll take a look at router 1 and router 3's OSPF interfaces, GI01, with the show IP OSPF interface GI01 command. First, router 1. We can see the router ID is the highest IP address on this router because a router ID is not configured. Its state is BDR. And all routers have the default priority of 1 seen here. And here we can see we are adjacent with the neighbor that is the designated router. Let's take a look at it next. Let's see the interface IPs. Same IP that was showing up as designated router on router 1. Now the show IP OSPF interface 01 command. Here's the IP address for the LAN network configured on the interface. And we see the highest IP address configured being used as the router ID. It has the default priority of 1. And its state is DR. Let's check router 2 and router 4. We should see a similar set of DR and BDR for its LAN network. First, router 2 and its IP addresses. Then the show IP OSPF interface GI01. Here we see the network type as broadcast. Its router ID is the same as its highest IP address. And its state is BDR. Now let's check router 4. IP addresses first so we can see router ID matches highest IP. Now the OSPF interface for the LAN. And we see that the router ID is the highest IP address configured. We see the state is DR. And it has the default priority of 1. And lastly, the backup designated router. But let's say we don't want routers 3 and 4 to be the DR for each of their networks, and we want routers 1 and 2 instead. Then we need to change the OSPF priority, and that's what we will do next. Router 1. We need to set the priority higher than 1, and we will do that under the interface configuration with the IP OSPF priority command. We can set the priority 0 to 255. For this exercise I will make it 10. And I'll do the same for router 2. Let's see the change in DRs. Wait, what? No change. Why? Because we first need to clear the OSPF process on all the routers so it initializes a new election. We do that with the clear IP OSPF process command. Say yes when prompted. The OSPF processes have been cleared on all routers. Now when we check routers 1 and 2, we will see they have become the designated routers. Now let's run debug on OSPF packets. This will give us a look at the communication between the routers running OSPF. If I'm debugging to the console and not a syslog server, I run the undebug all command first. This is so, with one up arrow and hitting the enter key I can turn off debugging, should it start to overwhelm the console. Let's run debug IP OSPF, here we can see all the options. We will use packet. Here we see the debugging output on the console. That's enough. I hit the up arrow then enter and all debugging is stopped. Let's dissect some of the output. Here is our OSPF process of 100. Here is the interface the packet is being seen as and it's coming in. The IP of the router sending it. And the OSPF multicast address it's being sent to. OSPF version 2, then type 1 refers to the packet type, 1 for hello. Len 48 is length of packet in bytes. RID is router ID and area is 0. And just off screen there is also a checksum value to verify the packet, and an auth method with 0 being none, 1 being plain text and 5 being MD5 digest. Let's recap. We discussed what is OSPF. We discussed OSPF router types, OSPF LSAs, and OSPF areas. We configured OSPF with a single area. Area 0. We went over designated router and backup designated router and how to configure them. We ran debug on OSPF packets and took a look at the output. And always, document. Thanks again for watching this video. Please give a like and subscribe so you will be notified when more videos are uploaded.